Classification of elements and periodicity in properties. The periodic table is arguably the most important concept in chemistry, both in principle and in practice. It is the everyday support for students. It suggests new avenues of research to professionals, and it provides a succinct organization of the whole of chemistry. It is a remarkable demonstration of the fact that the chemical elements are not a random cluster of entities but instead display trend and live together in families. And our awareness of the periodic table is essential to anyone who wishes to disentangle the world and see how it is built up from the fundamental building blocks of chemistry, the chemical elements. Glenn T. Sheborg. In this unit, we will study the historical development of the periodic table as it stands today and the modern periodic law. We will also learn how the periodic classification follows a logical consequence of the electronic configuration of atoms. Finally, we shall examine some of the periodic trends in the physical and chemical properties of the elements. Why do we need to classify elements? We know by now that the elements are the basic unit of all type of matter. In 1800, only 31 elements were known. By 1865, the number of identified elements had more than doubled to 63. At present, 114 elements are known. Of them, the recently discovered elements are man made. Efforts to synthesize new elements are continuing. With such a large number of elements, it is very difficult to study individually the chemistry of all these elements and their innumerable compounds individually. To ease out this problem, scientists search for a systematic way to organize their knowledge by classifying the elements. Not only that, it would rationalize non chemical facts about elements but even predict new ones for undertaking further study. Genesis of the periodic classification. Classification of elements into groups and development of periodic law and periodic table are the consequences of systemizing the knowledge gained by a number of scientists through their observation and experiment. The German chemist John Daubernier in early 1800s was the first to consider the idea of trends among properties of elements. By 1829, he noted a similarity among the physical and chemical properties of several groups of three elements triad. In each case, he noticed that the middle element of each of the triad has had an atomic weight about halfway between the atomic weight of the other two. Table 3.1. Also, the properties of the middle element were in between those of the other two members. Since Daubernier's relationship referred to as the law of triad seemed to work only for a few elements, it was dismissed as coincidence. The next reported attempt to classify elements was made by a French geologist A.E.B. de Cancourtois in 1862. He arranged the then known elements in order of increasing atomic weight and made a cylindrical table of elements to display the periodic reoccurrence of the properties. This also did not attract much attention. The English chemist John Alexander Newlands in 1865 propounded the law of octaves. He arranged the elements in increasing order of their atomic weight and noticed that every eight element had properties similar to the first element. The relationship was just like every eighth note that resembles the first in octaves of music. Newland's law of octaves seemed to be true only for elements up to calcium, although his idea was not widely accepted at that time. He, for his work, was later awarded Davy Medal in 1887 by the Royal Society, London. The periodic law as we know it today owes its development to the Russian chemist Dmitry Mendeleev (1834 to 1907) and the German chemist Lothar Meyer (1830 to 1895. Working independently, both the chemists in 1869 proposed that on arranging elements in the increasing order of their atomic weight, similarities appear in physical and chemical properties at regular intervals. Lothar Meyer plotted the physical properties such as atomic volume, melting point, boiling point against atomic weight and obtained a periodically repeated pattern. Unlike Newland's, Lothar Meyer observed a change in length of that repeating pattern. By 1868, Lothar Meyer had developed a table of elements that closely resembles the modern periodic table. However, his work was not republished until after the work of Dmitry Mendeleev, the scientist who is generally credited with the development of the modern periodic table. While Daubernier initiated the study of periodic relationship, it was Mendeleev who was responsible for publishing the periodic law for the first time. It states as follows: the properties of the elements are the periodic function of their atomic weight. Mendeleev arranged elements in horizontal rows and vertical columns of the table in order of their increasing atomic weight in such a way that the elements with similar properties occupied the same vertical column in group. Mendeleev's system of classifying elements was more elaborate than that of the Lothar Meyer. He fully recognized the significance of periodicity and used broader range of physical and chemical properties to classify the elements. In particular, Mendeleev relied on the similarities in the empirical formulas and properties of the compounds formed by the elements. He realized that some of the elements did not fit in with his scheme of classification if the order of the atomic weight was strictly followed. He ignored the order of atomic weight, thinking that the atomic measurement might be incorrect, and placed the element with similar properties together. For example, iodine with lower atomic weight than that of tellurium, group 6, was placed in group 7th among along with fluorine, chlorine, bromine because of similarities in properties. At the same time, keeping his primary aim of arranging the elements of similar properties in the same group, he proposed that some of the elements were still undiscovered and therefore left several gaps in the table. For example, both gallium and germanium were unknown at the time Mendeleev published his periodic table. He left gap under aluminum and a gap under silicon and called these elements eka aluminum and eka silicon. Mendeleev predicted not only the existence of gallium and germanium but also described some of their general physical properties. These elements were discovered later. Some of the properties predicted by Mendeleev for these elements and those found experimentally are listed in table 3.3. The boldness of Mendeleev's quantitative predictions and their eventual success made him and his periodic table famous. Mendeleev's periodic table, published in 1905, as is shown in figure 3.1. 3.3 Modern periodic law and the present form of periodic table. We must bear in mind that when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. However, the beginning of the 20th century witnessed profound developments in theories about subatomic particles. In 1913, the English physicist Henry Moseley observed irregularities in the characteristic X-ray spectra of the elements. A plot of under root uh, nu, where nu is frequency of X-rays emitted against atomic number Z, gave a straight line and not the plot of under root nu versus atomic mass. Here he thereby showed that the atomic number is a more fundamental property of an element than its atomic mass. Mendeleev's periodic law was therefore accordingly modified. This is known as the modern periodic law and can be stated as the physical and chemical properties of the elements are periodic function of their atomic number. The periodic law revealed important analogies among the 94 naturally occurring elements. Neptunium and plutonium are like actinium and protoactinium are also found in the pitch blende, an ore of uranium. It stimulated renewed interest in inorganic chemistry and has carried into the present with the creation of artificially produced short-lived element. You may recall that the atomic number is equal to the nuclear charge, number like number of protons or the number of electrons in a neutral atom. It is then easy to visualize the significance of quantum numbers and electronic configuration in the periodicity of elements. In fact, it is now recognized that the periodic law is essentially the consequence of the periodic variation in electronic configuration, which indeed determine the physical and chemical properties of elements and their compounds. Numerous forms of periodic table have been devised from time to time. Some forms emphasize chemical reaction and valency, whereas others stress the electronic configuration of elements. A modern version, so called long form of periodic table of elements, figure 3.2, is the most convenient and widely used. The horizontal rows, which Mendeleev called series, are called periods, and vertical column groups. Elements having similar outer electronic configuration in their atoms are arranged in vertical columns referred to as groups or families. According to the recommendations of the International Union of Pure and Applied Chemistry IUPAC, the groups and are numbered from 1 to 18, replacing the older notation of groups first A to 7th A, 8th, first B, 7th B, and 0. There are although 7 periods, the period number corresponds to the highest principal quantum number n of the elements in the period. The first period contains 2 elements. The subsequent period consists of 8, 8, 18, 18, and 32 elements respectively. The 7th period is incomplete and, like the 6th period, would have a theoretical maximum. On the basis of quantum numbers of 32 elements in this form of the periodic table, 14 elements of both 6th and 7th periods, lanthanoids and actinoids respectively, are placed in separate panels as at the bottom. Thank you.